Hello, welcome to another stream. Hello, welcome. Hello, Sasalawa 23, Mr. Botko, go on the third, Stop Gaming, Lord of Chaos, Cat, Kasha, go on the third, Guduk, Kostik, Yetanasov. Hello, welcome. So today is Sunday, if I'm not mistaken. Yeah, it is Sunday. Hello, Duke Yo Swag and Madman DTT. Thank you so much for 50 bits. Thank you. So today is Sunday, and that means today, according to the schedule, we're supposed to be doing game development, but on Friday we started a pretty interesting topic of Cellular Automata, and I actually continued that topic yesterday, and I kind of want to continue today as well because it's a very interesting topic. The idea of that topic was to explore different cellular automata, implement them in C and see how they behave, and so on and so forth, also visualize them. And yeah, it actually turned out quite well. We explored a bunch of them, and visualizing them was actually rather interesting. Alright. So let's actually take a look at what we have here. So it's going to be Automata. So we can find the source code of everything we've done so far on GitHub by project command or today command. And let me double check if I didn't fetch everything recently. So I think I fetched everything. Alright, I'm going to rebuild everything. So far we looked into 4 different cellular automata. So the first one is the famous one, Rule 110. So this is how it looks like. Basically, it's one-dimensional cellular automata, right? And each row in this grid represents the state of it, and the next row is the next state of the row based on the previous one. And this is how it evolves over time. Right, so basically we match the pattern of 3 cells, and based on 3 cells we compute the next one. And yeah, this is the evolution of this cellular automaton. So it's the simplest one. It's also Turing complete, by the way. So interesting fact, the Turing completeness of HTML5 plus CSS3, I think it was demonstrated by implementing Rule 110 using only HTML5 and CSS3. So if you have some sort of a computational system and you can implement Rule 110, your system is probably Turing complete. I think it's Turing complete because the Rule 110 is Turing complete by itself. So the other cellular automata that we explored was Game of Life. Classic one. We can probably add more things in here, right, so to make it just to do things more. There we go. It's a classical Game of Life, nothing special. Yeah, it just pops around sometimes, causes chaos, and then it will probably settle down at some point. Yeah, it just settled down. Alright, so and another one less known is Seeds. So this is how it looks like. So in Seeds, the rules of Seeds are way simpler than the rules of Game of Life, but if you cause a little bit of chaos, it will turn into madness, actually. Look. So this is how easily it just turns into a complete fucking like chaos. Yeah, but at the same time it's super easy to create gliders in it, right? So this is the simplest gliders in the rules of Seeds, and it just moves in the direction you actually draw it. You can draw it in any direction and it will move specifically in that direction, right? And there's a lot of other stable patterns in the game of Seeds, and it's actually pretty interesting. It is actually very interesting. So, and then it will turn into chaos at some point. Yeah, as you can see. So there's another similar to Seeds cellular automata. It's called Brian's Brain, and this is the first cellular automaton that we looked into that had more than 2 states of cell. So far, cells were basically in 2 states, on and off, dead and alive. This one has 3 states, on, dying, off, and this is how it looks like. So basically the black cell is empty, it's dead, the pink cell is alive, and the blue cell is dying. And it creates beautiful patterns, actually. It's actually super cool. And the rules are pretty much the same as the rules of Seeds, except it has additional cell dying, which prevents spawning new cells. And yeah, so It's actually super cool. I really like this one. Yeah. And it's basically, we started with a completely random state of the board, and it creates all of these patterns by itself. Literally by itself. We didn't do anything special. We just coded those rules and it just creates these beautiful patterns. And it's just fucking amazing. I really love it. Yeah, and we created like a pretty cool framework to code your own lifelike cellular automata. It looks like this. If you take a look at the source code of the Brian's brain, right? So to code Brian's brain, what you need to do, you need to define how many states of cells do you have, the mapping between the state of cell to the color, the rules of computing the next cell, and you just have to put all of that together and do live go, and it will just, you know, start playing that specific cell automaton. So you don't have to specify too much, and it automatically implements the user interface, user controls, right? So for example, you can pause everything, you can then click and add some additional cells in here, and that is implemented for you. You just have to like use this framework, provide some rules, and it will just automatically work like this. So it will simplify creating more cellular automata in the future, right, as we go. Because a lot of cellular automata that we're gonna look at today are based on life, and yeah. As a matter of fact, we have like a hierarchy of frameworks. So at the top of the hierarchy, we have a core framework, which basically provides the basic functionality for the interface, like it creates a window, organizes event loop, provides rendering capabilities, synchronizes the next generation loop. It doesn't assume any specific cellular automaton or the grid it's living on, you see? So basically, if you have some cellular automaton and it's not, for example, square, you can use the core framework because it doesn't assume any grid. Right, it just assumes that you have a state and that the next state is going to be generated over like, you know, regular periods of time. So that's the only thing it assumes. So the next framework that is based on the core is called square framework, right? It includes core and it extends it, and basically it assumes that your cellular automaton lives on a square grid. Not a hexagonal one, not a triangular one, or any kind of grid, square grid. Right, and it provides you basic like functionality specifically for that. You can specify the actual size of the grid, and it automatically computes the sizes of the cell. It provides you functions to fill a specific cell by row and column, so you don't have to do the math, and so on and so forth. And based on that framework, we have life framework for cellular automata that are lifelike, right? Where basically you compute the next state based on its neighbors. And using that framework is actually super easy. You just have to provide the basic rules, the mapping between the state of the cells, the color, and the framework will do everything for you. If for any reason this framework is not suitable for you, you can just go one abstraction layer back and implement something else. And this way we can build like a hierarchy of these frameworks. So you see what I mean here? So this is basically what we build. And it's actually pretty convenient because it helps us to iterate really, really quickly. So let me actually draw the hierarchy for you. Did I start my life? My paint? I don't remember if I started my paint. Because it actually takes so much time to start it. Yeah, so okay, it's starting, hopefully. All right, so we start with the core, right? So here's the core. Then we have square, which sort of inherits the core, and then we have a life. So the reason why I did it like that is that in the future I'm thinking that maybe we're gonna have cellular automaton based on hexagonal grid, right? And in that particular case, as you can see, is gonna actually extend core, but not square, because square kind of, you know, conflicts with hexagonal grid, right? You're gonna have like different derivatives of that core framework for different sort of grids. How did you get that my paint layout? I don't remember. I messed with it several times. So you can actually have these kind of like things. You can click on things around and you can just get it to this particular state. I don't remember how exactly I get there. All right, so hopefully all of that makes sense, and we have a list of cellular automata that we wanted to look at. Let me see. So here's the list. So far we looked only at 4 of them, and we have 3 to go. If any of you have any suggestions for more different cellular automata, feel free to post them in the chat, and maybe if we have time, we can take a look at them. So yeah, I'm super proud of what we've built so far, so let's continue. The next cellular automaton is Wire World, which is extremely goddamn interesting, not gonna lie. So essentially you can emulate like electronics with this cellular automata, but on top of that, it's from the Life family. Yes, it's a cellular automaton from the Life family with which you can simulate electronics and like movement of electrons and stuff like that. So that means we should be able to use our Life framework and it will just work, apparently. Anyway, so this is how it looks like. Right. So this is a wire and this is like a 2 diodes. So diode basically allows the electrons to move in one direction but not in the other, and that's exactly what's going on. So a single electron is just red and blue, and it can actually move, you know, in one direction but not in another direction. So it's a cellular automaton first proposed by Brian Silverman. Brian Silverman is like really famous in a world cellular automata. So in 1987, as part of his program Phantom Fish Tank. What is a program Phantom Fish Tank? Never heard of it. And there's no references about that in Wikipedia, by the way. Game review Phantom game review. It's a game? Hello Banana Wave YouTube, welcome to the stream. Playing time and number of players vary. It is software written for Apple II series of computers that gives the user a chance to construct and explore universes based on John H. Conway Game of Life. Holy shit! So Brian Silverman was also a game developer. Nice, Phantom Fish Tank. It's pretty cool. Alright. So it subsequently became more widely known as a result of an article in the computer recreation column Scientific American. It's particularly suited for simulated transistors, and Wire World is Turing complete. So a wire world cell can be in one of 4 different states, usually numbered 0, 3. So the Brian Brains was the first one with 3 states, 3 different states of the cell. This one is 4 states of the cell. So, and our framework can actually handle that. It can actually handle that. So modeled by colors, for example, 0 is empty, electron head, electron tail, and conductor. As an all-cellular automata, time proceeds in discrete steps called generations. Cells behave as follows. Empty becomes empty, electron head becomes electron tail becomes becomes conductor. Conductor electron head if exactly 1 or 2 of the neighbor cells are electron heads, otherwise remains conductor. So Wire World uses what is called Moore neighborhood. Okay, we know what is a Moore neighborhood, nothing special in here. And yeah, so you can do pretty awesome stuff in here, as you can see. So there is like a LED number thingy. So at some point it will actually light up, I suppose, a particular, you know, particular number. So yeah, there we go. I wonder if we'll be able to simulate that in our own software. So that's pretty cool. Look at that. Ah, that's actually so awesome. I really like that. So we definitely need to implement this thing. We definitely need to implement it. All right. So Wire World. Wire World. So wireworld.c. So, and let me quickly include this entire thing. Let me quickly include it. So we're gonna include life, right? Live.h. And as already mentioned, we have only 4 states of that cell. So it's gonna be enumeration. It's gonna be wire world cell. It's gonna be empty. It's initially empty. Then we have E head, I suppose, electron head. Maybe just call it head, then tail, and then conductor. There we go. And I also want to introduce something like cell count as additional variable that will tell me how many of the states we have, and it's usually very convenient to have that constant lying around, so you can actually refer to it in different places. So now we need to map each individual state to a caller. So we're gonna have something like cell caller, and the size of this specific array is gonna be cell count. Right, cell count, like this. And let me put this entire stuff like that. Two, and boom, equal. And let's actually choose the colors now. So empty is gonna be background color, so it's gonna be black. Head is supposed to be what? It's supposed to be blue. I think in our style we have a blue color. Yeah, we have a blue color. Then the tail is red, which is going to be pink color, so we have a pink color. And let's actually introduce yellow color, but we don't have it yet, so I think I'm gonna do it like that. So it could be something like FF. I think it's a red and green, and yeah, let's put it like this. So this is gonna be our yellow color. So, let's continue. So now we also need to define a rule. Right. So life rule, it's a simple function, right, that takes the current state of the board, the current row and column of the cell for which we're trying to compute the next state, and we need to define it. So it's going to be wire world rule, right? And let's actually not define it yet. I'm gonna just take and return this cell as it is right now, just to see how it's gonna go. Okay, cool. So this should be enough to define this cellular automaton. Well, not really enough. We still need to code the rule, but I wanna just see how the colors look like. All right. So live.h, live go. So this is how we're gonna execute it. So first we need to provide the initial state of the board. I'm gonna go with the empty board, because like we're not gonna fill it with anything yet. So the rule is gonna be wire world rule. So the amount of cells we have at cells count, and the mapping for the color is the cell color. Okay, so we provide all of that information to the framework, so the framework knows how to render everything, how many states of the cell to expect, and so on and so forth. And that's it. So yeah, it's actually as simple as that. You don't need to code any of the interfaces, it's already provided for you. Alright, so let's actually do something like make B. I have to actually add wire world to the build system, and let's try to rebuild that. And it doesn't compile because I did a small fucky-wacky. Yeah, I forgot to call it yellow. I just copy-pasted the name, but I forgot to call it yellow. Yeah, I see. So cells, did I call it cell count? Yeah, I think I should have called it cells count, but whatever. Doesn't really matter that much. Yep, it seems to be working. Let me actually go to the square and decrease the amount of rows and cells and make it 10 by 10. So they're going to be more visible. And then we can try to play with them. So this is going to be wire world. And in here we have, you know, these cells. And what's interesting is that you can scroll through them. So yeah, you can scroll through them and you can specify different things in here. Right now, if I try to run it, nothing is going to work at all because we haven't coded the rule. Let's try to code the rule. Wire world, and it's going to be switch, and it's going to be based on the on what? on the cell itself, right? On the cell itself. So let's actually see. So we have 4 types of cell. So if it's empty, we just return empty, nothing special. If it's head, we return tail. There we go. If it's head, we return tail. If it's a tail, it becomes conductor. Becomes conductor, and if it's a conductor, we are going to do the following thing. Electron head if exactly 1 or 2 of the neighboring cells are electron heads. Okay, so that means we need to count the neighbors, right? We need to count the neighbors. So neighbors, there we go. So neighbors, and so this is gonna be previous, and we start at row. We start at row, start at column, and what exactly we count in electron heads, like neighbor heads. There we go. So this is the neighbor heads, and head if exactly 1 or 2 of the neighboring cells are electron heads, otherwise it remains that. Okay. Neighbor heads is equal to, or neighbor heads equal 3, that means it also becomes a head, otherwise it remains a conductor. There we go. On top of that, it probably makes sense to make a default thing where we're gonna do assert, saying something like via world rule unreachable. There we go. And if we try to compile this entire thing via world, okay, so this is int, there we go. Assert, we need to also include assert. Cool. Let me now try to run this entire thing. And yeah, so I'm gonna pause it and let's try to code one of those things, right? Let's try to code one of those things. So we have something like this, right? But we have it in the form of a conductor, so we have to keep scrolling through them until we have a conductor, right? And then we have this wire, right? We have this wire. And all of that has to be a conductor as well. So let's actually make it a conductor. If I try to run it, it stays the same. So now the head is blue. Let's actually try to make this a head, and let's try to make this a tail. And nothing happened, apparently, which is kind of interesting. Did I fuck it up? Yeah, I probably fucked it up. Maybe it has to be... Oh yeah. Like this. No, it moves in different direction and it actually didn't even do anything. Huh, that's really strange. So empty is empty. Empty is empty. Head, tail, tail, conductor, conductor. Exactly 1 or 2 of the neighboring cells are electron heads, otherwise remains conductor. So we count specifically electron heads. If this entire thing is exactly that or that, might as well actually try to wrap that thing around here. It's gonna be head. You're checking if it has 2 or 3 numbers, but it should be 1 or 2. Really? 1, yeah, 1 or 2, thank you. I guess my brain couldn't process it properly. Would be kind of convenient if we could actually not scroll through all of these things. But oh shit, what the fuck just happened? Oh, this is because it wraps around, I see. Yeah, that makes sense. And because it wraps around. That's totally fine. Yeah, so it's probably gonna go in a different order, okay. So that has to be like this, and there we go. So it just, yeah. Which is kind of interesting. Can we actually make it loop through itself? Huh. Oh. That is so cool. Once you... Okay. And guess what's gonna happen once we close the loop here? Oh shit. I didn't expect that. Oh fuck. I really didn't expect that. And oh, it doesn't even stop. Seriously, it doesn't even stop. That's so cool. I like it. Interesting. So basically, it's like short-circuited itself, right? I suppose. Basically, short-circuited itself. That's so cool. I really like that. Yeah, short-circuit. Literally short-circuit. It's a feature now. Yeah, probably. I wonder if there's more interesting things you can have there, and of course we could probably slow down the speed of the generations and stuff like that, because right now it's fucking enormous. Right, we can actually make it a little bit slower, but that will require rebuilding. Wild world. There we go. I wish I could see the actual grid things, but I think it's too much to ask. Yeah. Okay, so what's funny is that, yeah, it's super easy to create more wires, because once you create like electron hat, it will cycle through all the states and become conductor. You don't even have to do anything. That is so cool. I really like that. But at some point, like, some of the things are not really possible to do anymore. And it's not gonna settle, apparently. I think it's not gonna settle. Yeah, it keeps generating this kind of stuff, and yeah. So I wish we could build something like this. I think that would be actually kind of cool. But the question is, how can we build that? And is there any other interesting pattern that we can try to run? Okay, so there's a wire world on Rosetta code, computer in Java. No wires contains the interactive wire world environment. So to create a program that reads the wire world program from file and displays an animation proceeding. Okay, so it's cool. There are descriptions of this thing, but there's not that many interesting patterns that we could look at, if you know what I mean. Right. So maybe we can do the following thing. I'm gonna go to the square, and actually gonna increase the size of the grid. To be fair, I want to be able to see the grid though, but the grid becomes kind of like pointless when you have too many cells, you know what I mean? Right, so maybe when you have like a cell width and height of a certain size, over like smaller than certain threshold, the grid disappears. But if it's bigger than a certain threshold, we actually draw the grid so we can actually see what's going on there. Right, so yeah, so I think I ran the wrong thing, and I need to rebuild everything. So this is one of the things we can try to do, at least. Yeah, because now it's kind of cool how it generates this kind of thing. Boom, 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 boom. I really like that. Okay, so let's actually commit whatever we have. Wild world, and let me see. So what do we have here? So we have that. Add wild world cellular automaton. I'm gonna push that right into the repo. So, and what I want you to do, I want you to introduce the grid. Right. So the grid is going to be implemented on the level of the square framework. So when we begin the rendering, we render the core, and the next thing we want to do, we want to render the grid. So render the grid. Let's see how we can do that. So we're going to render the grid by actually going in discrete intervals and just rendering the lines, right? The lines. The question is, how can you draw a line? I think that should be done on the level of a core framework, because in the core we have a field rect, right? And we need to introduce something like core draw line, which accepts the core context, and then it also accepts x1 y1, and then it's going to be x2 y2, and it also should accept the color with which you want to render all of that, right? So something like this. So now, how do we draw the line? So SDL draw line. I keep forgetting how to do that, and what's the function that is used for drawing the lines. So this one is pretty straightforward, I think. The only thing we'll have to do, we'll have to florf all of that, and we also have to set the color. Yes. So we'll have to take the renderer. We have to take the renderer from the context. We have to take set the current drawing color. And now what we have to do here, I might as well actually do the following thing, where I just, you know, just do something like that. I think it's kind of cool. Florf like this, and then something like this, and there we go. So, and now we have a function that allows us to draw a line. Now, in a square framework, on the level of a square framework, we can use all of that, right? So we're going to be iterating by each individual row. A row starts with 0, and then until we exhausted all of the rows. And in here, we're going to draw the what? We're going to draw the line. So what's going to be the color of the line? That's a very good question. So it's going to be context core. So X. So since we're drawing rows, the only thing that's changing here is Y. So that means it's going to be something like row multiplied by cell height. There we go. And X is going to be different. So initially X is going to be 0, but then it's going to be what? Screen width. Something like this, I think. So this draws all of the rows. It draws all of the rows. So let's try to execute that and see what's going to happen. So something went horribly wrong, because so I have to extract the renderer from the context. So what else do we have here? uint color, it's just a color. Yes, and why do I have this as a uint? In the core, if I it has to have the type color, and the type color is alias to uint32 anyway, right? As you can see, it's just a type def. So what else? So color. So what we're gonna have as a color for the foreground grid, I'm not quite sure. So I know that I took colors from my theme that I use in Emacs because I really love it. So maybe I'm gonna steal something from that theme as well. So let me see. So we have a background. We can just make the background slightly lighter, and that's actually a pretty good idea. So we'll just make it slightly lighter than the current background, and that should make it, hopefully. So this is going to be grid color, and where is the square? Yeah, it's going to literally called grid color, and let me see if it's going to work. And it doesn't work. It doesn't do anything. Thank you very much. I wonder why though. Did I fuck it up somehow? Maybe I did in fact fuck it up. So what if I make the grid pink so we can instantly see that something went wrong? Okay, so something definitely went wrong. So they kind of like go in dots, and I feel like I really screwed something up. So X, Y, x1, y1, x2, y2. Maybe I screwed up somewhere in here. So draw line. So x1, y1, x2, y2. I don't see any problems whatsoever, but they're still there. That's very strange. Does anyone see any problem? I don't see any problem. So cell height. Huh? Excuse me. What the fuck? Like, I literally don't see any problems. Like, what the fuck? If it's equal y1 equal 1, 2, it's not dot. It's not dot if x's is different. And x's are different. x1 is 0, x2 is width. No. No, excuse me. That's kind of the point. And so something very, very dumb, and it drives me nuts. Like, you make some small mistake, you don't see it, you become completely blind to it. No matter how much you try, you won't be able to see it unless somebody else notices it. And you might as well just quit programming, right? You might as well just quit programming because you're so fucking dumb. And holy shit. Okay. Gap is cell height. Gap is cell height. Might as well. But it still like draws these lines and whatnot. Is it screen width? Is it really screen? Okay, let me actually make it like 100 in here. Okay, 1000. What is going on? What is going on? Am I going crazy? Am I literally going crazy? No, what the fuck? Nothing makes any fucking sense. I use this function so many times. What the hell is going on? Okay, let me try the following thing. Core draw line context core. So 0, 0, screen width, screen height. Screen width, screen height. What is going on here? And it's gonna be a pink color. Okay. So it is incorrect. Alright, so the function itself works incorrectly because that should give you the right thing. That should give you the right thing. So if I go to the core, so I set the color correctly. So floats, that shouldn't be... Okay, let me try to directly take this entire code and use it instead of the other thing. So let me see. So this one has to be 0, this one has to be 0, this one has to be screen width, like screen width. Do I? Yeah, row should be alright. Hello Mizi, welcome to the stream. screen height. What did I do wrong? What did I do wrong? I don't understand. Core. Let me see. Is it gonna work now? So something doesn't compile. It's part of the core. It's part of the core. So the color is gonna be pink, whatever pink color, use the pink color. And yeah, okay, so this function doesn't work correctly. What the hell is wrong with this function? Is it because the screen width and screen height are incorrect as well? Okay, there are dots, there are clearly dots. Do I have somehow set the style wrongly? I just discovered the most bizarre bug. Is it possible that the grid and the rest of the rendering overlap? What is the rest of the rendering? There's no rest of the rendering. There's no such thing as rest of the rendering. It's literally empty. There's literally nothing drawn on the screen. Unless there is. Unless there is. Yeah, it's basically specifics of how our framework works, I see. Essentially, it actually draws empty cells always. It draws the empty cells always, no matter what. And because they have a background like alpha non-zero, they actually, yeah, that's actually a pretty interesting way to shoot yourself in the foot. Essentially, you're thinking that there is nothing is drawing right now, but there's actually something drawing. So yeah, I created a situation where on an empty cell, an empty scene where nothing is drawn, there's still something drawn. Interesting. Okay. Because of that, maybe I should always set the off cells for the for all of the examples as transparent. So empty cell is always going to be transparent, and that's going to be the point, right? It's always going to be transparent. So here is that. So another one is going to be a rule 110. So the color here is not going to be background. All right. So where's another one? So the another one is goal, and it's going to be something like this: goal, then seeds. Then seeds, then BBC. So this is the background color. And then we have a wire world. We have a wire world, yeah, which I already made like this. Okay, so that makes sense. That makes sense. And why I didn't recompile everything? I think I wanted to recompile literally everything, just in case. We need to compile. Okay, so let's actually go ahead and implement the grid and see how it goes. So that should work now, right? So we can remove that thing, we can remove this thing. So this one is going to be screen width. Okay, so that gives us this thing. So also we're gonna only rebuild only wire world, right? And I think it would make sense to start from 1 to actually not show the last thing. Yeah. And similarly, we can now implement int column starting from 1 column less column. Hello, John. welcome to the stream. Hello, hello. And let's do core draw line. It's gonna be context core. And so how we're drawing everything. So the x is gonna be column cell width. This is gonna be 0. Then column cell width, and this is gonna be screen height. This is going to be screen height, and that's pretty much it. And we're going to use the pink color as well, and